point out a few things. As far as atmospheric refraction, atmospheric gradient, things like that, different variations in air density, those things, I don't say that those things don't exist. I've never said that those things don't occur. Those are scientific facts. I've seen where I would look down a highway, and at the end I would see the waves while I'm driving on a hot day. I've seen that. I know that the air temperature and the temperature of the surface causes a variation in the atmosphere wherein the density is shifting, and it would affect light. I've never said that those things don't exist. And if you believe that I've said that those things don't exist, and if you've ever said that I've said that those things don't exist, I defy you. Go find the video where I said that atmospheric refraction, atmospheric gradient, and all that, light dispersion, beam divergence. Go to the video, timestamp it, come back to me and tell me when I said that, and I will send you $500. Until then, I'm going to need you to stop saying that. Flat earthers do not discount science as a whole. We embrace science. We practice science. We respect science. What we don't respect, what we don't appreciate is the theoretical science that's being passed off as fact. We don't appreciate theories being taught as truths, like gravity, that has yet to be proven. Black holes, you've never experienced that in your reality, so it doesn't count. Dark matter, dark energy, they still don't know what this is, and so it's just theory at this point. These are the things that we dispute. So don't misunderstand. We don't discount all science. We discount the things that you have to believe in, the scientism. That's what we discount. Now, what is atmospheric refraction? Atmospheric refraction is the deviation of light or other electromagnetic wave from a straight line as it passes through the atmosphere due to the variation in air density as a function of height. Now, recently, Jerry did a laser test of his own in his backyard that demonstrates atmospheric refraction. And for some reason or another, people keep linking me back to this video as if it actually explains away what we saw in our laser test. So let's take a look at this video and chop it up.
In his demonstration, he had a cheap laser clamped down into a vise, firing at a board that was 40 feet away. The air temperature was 86.2 degrees. And we're going to say, for the sake of argument, that the tray of ice water, the temperature there is about 35 degrees. Slice the tray of ice water under the laser. You see the laser bend downward ever so slightly. Does it again. You can see it go downward slightly. And he has a hot pan that he's left in the sun. You see it slip under there, and the beam goes upward a little bit. Slips back, does it again. You see the beam refract upward ever so slightly.
Now, during his test, his air temperature was 86.2 degrees. Let's say his water temperature was around 35 degrees. That gives a temperature variation of 51.2. During our laser test, our air temperature was 68 degrees. And our water temperature was 55.4 degrees, giving us a temperature variation of 12.6, thus giving us the perfect conditions to create little to no atmospheric refraction due to temperature variation. The temperatures weren't at odds enough to actually create the atmosphere that would bend the laser sufficiently. Now, let's just take the numbers from his test and compare them to the numbers from our test concerning the air and water temperatures. Now, the variation of his was 51.2, ours was 12.6. Now, if we divide 51.2 by 12.6, that gives us 4.06. So would it be fair for us to say that we should, under his conditions, had our laser beam been as close to the water, under our conditions of air and water temperature, we could expect roughly 25% of the atmospheric refraction based on the actual temperatures. Is that fair? Can we say that? I think so. So that's a fail, actually. because it doesn't really match up with reality and the numbers are not on your side for that one. Now let's run the numbers from the curvature calculation from the laser test that we conducted. So our distance was 10.3 miles, times that by 10.3, that gives us 106.09. 106.09 times 8 gives us 848.72. You divide that by 12 to get feet, and you get 70.72 feet between the two of us of supposed curvature. Now let's take away 10 feet to make up the height of the laser, which I went out and got a good measure on. Actually, it came out to be a little less than that, but let's go ahead and say 10 feet. And here's the video just in case you don't believe me.
So for peace of mind, I went back and got a proper measurement of the laser's height at Mark's position. Now, as you can probably see here, the laser looks like it's tilted back, meaning it's added a couple of inches because I didn't level it when I put it in the rocks down there. Put it in the rocks where I would measure it from up on the boardwalk. So it came out to 24 inches even when it wasn't leveled. Looks like the laser was tilted upward. So then I tilt the camera up, showing my work that I place it up there. Walk the camera back up here, not breaking scenes. Set the camera down in the position it's going to be in. Get the laser all leveled. Adjust the camera. Grab the tape measure so I can get the proper measurement. Alright, drop the tape measure down to the rocks down below. Get the laser beam on that. Get a measurement. That came out to 81.5 inches. Now, all things considered, in getting the height of the laser, we have 24 inches above sea level and then 81.5 inches above the lower marker, giving us a total of 105.5 inches, or 8 feet 9.5 inches. But let's just go ahead and say 10 feet.
Okay, so you saw right there that the height of the laser is a little less than 10 feet high from what you could tell, but we'll just go ahead and say 10 feet. So we have 70.72 feet of curvature minus 10 for the height of the laser. That gives us 60.72 feet of curvature. And then we have the 60.72 feet of curvature plus 0.25. Now, I factor in 0.25 because there was a point during the live stream where I got my camera down right at sea level, but we'll just say it was 3 inches or a quarter of a foot. So that's 0.25, giving us 60.97 feet of curvature, factoring in the height of my phone. So let's see exactly how much curvature would have been compensated due to refraction from Jerry's test.
Now, this was crude, but that was a 12-inch section of cooler air affecting a laser enough to move it, what, a half a centimeter after only 40 feet?
Okay. All right, let's take into account that 8 feet. That still doesn't account for the other 52.97 feet of missing curvature, so we're just going to call that another fail. Now let's compare demonstrations. We have Jerry's demonstration where he had his laser beam about 12 inches away from the pan, the tray full of ice water and the hot pan that he had left out in the sun. So there was about a 12-inch gap where the air would be affected. So he said, okay, so the laser passes through this area. I just laid out the height of the laser from the water in that short video showing me making those measurements. So the distance on our laser test in comparison to his is actually 10 times. Our laser was 10 times the distance away from the water than Jerry's in his demonstration. So it really doesn't hold any weight, except for the fact that he said this.
So if you have a laser that's close to the surface of the water for miles, it's going to refract a lot.
Well, Jerry, in addition to the minuscule air and water temperature variation from our test in comparison to yours, we now have to factor in that our laser was 10 times further away from the water than yours was during your demonstration, thus making it far less likely that the beam would be affected by atmospheric refraction. Therefore, you have also failed in this particular area of discussion, sir. In your demonstration, you showed that the laser beam is affected by heat and cold. This is simple way to show refraction, which actually is a thing. Now, you showed that the heat causes the beam to refract upward, that the cold causes the laser beam to refract downward. Now, perhaps this would be relevant had we conducted our laser test during the part of the day when the sun was beating down onto a surface of bulging glacial water, but those days are kind of few and far between here in the Pacific Northwest. What you displayed doesn't really match up with reality in the least bit. So, concerning that degree of atmospheric refraction, being able to bend our laser over the water, that point is now null and void until you all can come up with a proper demonstration replicating what you believe to happen.
Do I think that refraction accounts for what you saw in your results? No. No. No.
All right, Globies, you heard discount Neil deGrasse Tyson. So cut the crap with that refraction argument. Anyway, let's see what else this guy has to say.
I'm going to talk about something you didn't account for and you probably never thought of. The divergence of the laser beam. That is the amount the beam spreads out over distance.
Now, in addition to his little backyard demonstration, Jerry also mentioned beam divergence and light dispersion. So we'll talk about those real quick. But let's first take a look at some footage that I took with my P900 during the live stream. All right, yeah. Right there. Yep.
Right there.
Yep. Right there. That's perfect. That is it. Yep. You're shining it right at me. Everybody can see it. Perfect.
I can see it in that box. I can't see it.
Now, I also took a little video showing the relationship between the observer and how the eye would react to a laser beam coming straight at it. Now I'm going to show you a quick demonstration of what happens when a laser beam interacts with the observer. So in this exercise, you are going to act as the observer, and we have a laser beam pointing right at you, dead center. Let's see what happens. Let's see if we see anything that looks familiar. Okay. All right, we have the laser. You'll take it to the right a little bit. You see the beam going to the right. You take the beam back to the left. And then when the beam's fairly close to the center, you see a familiar sight. You see the bright glow in the center, red right here, and then you see the red outline. Do you not? Does that not look like something you've seen before? Perhaps? So now, I'm going to show you what it would look like for bulging water to obstruct the observer and the laser. We'll see what happens when we introduce bulging water. So the only way that I could think to have actual bulging water was for it to be contained in this plastic bag. So I'm even going to flatten it out and we'll see what happens. So there's your laser beam. Get it to stop moving. There's your laser beam, restabilized. And now we introduce the bulging water, representing the curvature. Now if I bring it down even, I'll try to have just a little bit, but even a little bit of obstruction causes you to not be able to see the laser. Okay, there's your beam. There's your curving water. And you could not see it. So, simple lesson here. When there is obstruction between the observer and the laser, the beam cannot be seen. And now for a quick demonstration of light dispersion and its relationship to the observer. Light dispersion. the idea of the laser's beam spreading out so far that it would somehow or another curve itself over the bulging water to reach my eyes, the eyes of the observer, and still give such a bright light as we're looking at what seems to be the source of illumination. So I'll take this flashlight, my Blackhawk flashlight. Okay, you have this setting, it goes into a square, and then when you spread the beam out, that's as far as the beam will spread. So I'll go ahead and turn this around here. The beam is spread as far as it can go in order to exaggerate how much Jerry says that the beam should spread out, about 250 feet, he says. But once again, we have to consider the idea that light travels in a straight line, and this point of illumination, when obstructed, more than likely won't be available when it's behind the curvature of bulging water. So there's your bulging water right there, and you can't see the bright spot. Now, there may very well be some illumination above the head of the observer. However, the point of illumination is still out of sight when you introduce the bulging water. And that concludes this demonstration. Now that demonstration showed that light, regardless of how dispersed it becomes, and when fired at bulging water, still won't show that brightest point of exposure to the observer. Jerry, it's a laser, not a lighthouse with magical bending light. And wait a minute, didn't you say something about there being the appearance of a half circle?
A 7-foot height is about 3¼ miles out with no refraction on a perfect sphere. Well, by that distance, it will have spread out to some 85 feet. That means it has erased the distance to the horizon and is now a 85-foot wide half circle broadcasting from less than 7 miles away.
All right, let's take a quick moment to do a shape review for Jerry. This is a circle. This is a half circle. This is a circle. This is a half circle. Okay, now it's going to mix it up a little bit. Stay with me. This is a circle. This is a half circle. All right, you're going to do the next one on your own, okay? What's this, Jerry? A circle. Yay! Good job, Jerry. Yeah, that wasn't a half circle. We're going to go ahead and call that another fail. Let me explain why I speak so strongly about this laser test, why I skip over the whole idea of refraction. What you're seeing here is the beam from a 3,000 megawatt laser. I have first-hand experience with this particular laser. I know what it does. I know what it doesn't do. I know that this thing goes into a straight line because I have first-hand experience with this particular laser. Now let me ask you, have you ever dealt with a 3,000 megawatt laser, Jerry? Does this look like it would bend, Jerry? Come on, guy. Lasers don't do that. Think this bends? Are you kidding me? Are lasers not used to show that which is level? To keep a straight line? Lasers don't bend like that, man. We have to be honest with ourselves. The basis of your argument here is to talk people out of what they know is true in their existence. You're trying to convince people that water bulges on this imaginary globe that you believe that you live on. In addition to water bulging, which goes against what everyone experiences in reality, you're also trying to say that laser beams will also curve over the bulging water on this imaginary globe, when in actuality everyone experiences water in large quantities when left undisturbed. We observe with our own five senses, our sight, namely, that the surface is flat and level, generally. And also in reality, we understand that laser beams fire in a straight line. Are you going to convince people that they don't see what they see? How dishonest are you? Now, thus far, you have been unable to prove that which you believe. So we're going to call that another fail. So there was a time in your video where you spoke about how I'm a trendsetter and how people keep coming to you repeating the things that I say.
You are a trendsetter in a flat earth world. You say things that no one else is saying, or very few people, and suddenly everyone else starts to say it. You know this. You should take pride in it.
So that possibly being a factor, I'll go ahead and arm them with another question to ask concerning this whole laser test. And that question is, what part of the laser beam should not be visible do you not understand? And now to wrap this up. I've shown how atmospheric refraction was an incredibly insignificant factor concerning where the beam ended up during our laser test. I've shown how your particular demonstration of atmospheric refraction in your backyard, due to an only slight variation between the air and water temperatures, was nowhere close to what really happened. I've clarified the height of the laser above sea level, again demonstrating the insignificant effects of atmospheric refraction in our test. I've demonstrated how the laser interacts with the observer directly and indirectly. I've demonstrated how an exaggerated amount of light dispersion still doesn't cause the observer to see the brightest point of the light's origin. I've demonstrated that if there is obstruction between the observer and the laser beam, that the observer will not be able to see the brightest point of the light's origin. I've also given visual comparison of the laser firing directly towards the observer with and without atmospheric gradient. Jerry, your little laser test, because of the variables not matching my numbers, has nothing to do with reality. Your laser was too close to the tray with the ice water. The water temperature and air temperature was significantly more at odds in your replica demonstration than with our actual test. Those two issues alone blow away your argument over refraction. Now, if you're going to mock and ridicule my observations and claim that they're wrong, you need to replicate my numbers and carry out your operation under similar conditions. Thus far, you have failed to do so. So here's the bottom line. If the Earth is going to be determined to be spherical or flat, in either case, there needs to be some degree of measurable curvature. If there is no measurable curvature, we can only conclude that the Earth is flat. Now, thus far, you failed to provide an argument or demonstration to compensate for the remaining 52.2 feet of missing curvature. Now, until you do either of those things, you can consider yourself dispatched. Class dismissed. Nah, but for real though, you make sure if you come around talking about this laser test again, that you address that 52 feet of curvature. Otherwise, go ahead and keep your mouth shut.